Hello everyone, and thank you for attending this presentation. My name is Daniel Zhu, and I have the honor to present our article entitled Evidential Nearest Neighbours in Active Learning. So in the classical supervised machine learning, it's often necessary to train the classifier on a lot of training data in order to reach acceptable performances. This requires to label a lot of data, which can be very expensive, as quite often it is a human who do this labeling task. And moreover, it can happen that the oracle provides wrong labels, which can alter the classifier's performances. The active learning and the theory of Dempster-Shafer offer a solution to these problems, and in particular, in the article we submitted to the workshop, we propose to use a classifier based on the Dempster-Shafer's theory in active learning. So first of all, we will present what is active learning, the theory of Dempster-Shafer, and the classifier we are going to use, which is called Evidential Nearest Neighbour classifiers. And then we will present the experiments and the protocols. And finally, we will show the results we got and conclude. So the active learning is a paradigm of machine learning whose particularity lies in the building of a training set with only the most informative data. So at the beginning we have a lot of training data of unequal qualities, and after the active learning phase we have a subset which contains the most relevant data for the classifier. And therefore it is not necessary to label the whole dataset, we can just label the most informative data. So in this figure, we have a classifier which has been pre-trained with some data called bootstrap, and from its knowledge, the classifier will compute the informativeness of each training data. The most informative training data will be sent to the oracle, that's what we call a query, and the oracle will provide the label of the training data in return. The classifier will learn the labels and the data, it will update its knowledge, and it will do it again until the number of labels granted is consumed. And there are several ways to determine the informativeness of data. This is what we call the sampling method. One of the most famous sampling methods is the uncertainty sampling. Here again, there are several types of uncertainty sampling, but we will use the uncertainty according to the least confident sample. So the most informative data is the one whose the probability of classification on the most probable class is minimal, and this sampling method is used in the rest of the article. In the theory of Dempster-Shafer, there is a set called the frame of discernment. It contains every elementary hypothesis of the problem, and in our context of classification, it would be the set of the different classes. We will call it omega. And there are specific functions in this theory called belief functions. They are defined on this power set of omega, and their values are between 0 and 1, and in particular the basic belief assignment is an important belief function. It represents the elementary belief assigned to the hypothesis. And the basic belief assignment, BBA, verifies the normalization rule, which is given here. The core feature of Dempster-Shafer is the rule of combination of Dempster. So let us consider we have n BBAs of the same frame of discernment, and if we want to combine them, if we want to aggregate this function into one BBA, we can use the following formula. This rule has the specificity to enhance the hypothesis of omega, where the BBAs mk are in agreement, and although the rule looks difficult to compute, in practice a lot of values of the BBAs are null, which simplify the computation. The Dempster-Shafer theory offers the possibility to model the uncertainty and imprecision, which are often the cause of incorrect labels. And for example, let us consider a frame of discernment which contains only three hypotheses, A, B, and C. The value of M1 here is imprecise because the belief is assigned to a non-singleton element of the power set, and uncertain because the belief is partial, it is not 1. The value of M2, however, is precise because the belief is assigned to a singleton, and certain because the belief is total. Other beliefs are then necessarily null due to the normalization rule. Unfortunately, in our paper, we do not propose to model the oracle's uncertainty and imprecision. There is no classifier that does it as far as we know. However, it is still possible to take erroneous labels into account. So the classifier we are going to use is a variant of the classical k-nearest neighbors. It is defined with the BBAs of the Dempster-Shafer's theory, and we will call it EKNN for evidential nearest neighbor classifiers. This classifier, introduced in 1995 by Thierry Deneux, takes the distance between the data and the distribution into account. So first, we take the k nearest neighbors of X, the data to be labeled, and we generate a BBA for each of them, supporting the sole hypothesis that the neighbor and X are from the same class. If that's not the case, then we will put the rest of the belief on the ignorance. Then the rule of combination will be used among the BBAs supporting the same class, so we get one BBA per class, and finally these BBAs are combined together, so we have only one BBA. The hypothesis which has the most belief is the class of X. This classifier is, however, unable to model an imprecision because of its definition. Only one class is supported per neighbor, and moreover, it doesn't model the uncertainty of the oracle because there is no way for the oracle to quantify his belief with this classifier. However, we can expect a certain robustness against the wrong label, thanks to the rule of combination which is applied twice. For example, let us consider a frame of discernment with two classes, θ1 and θ2, and let us consider a sample X to be labeled and its neighborhood, which is represented by the circle. There are two scenarios in this example. Case A, X3 and X4 are correctly labeled by the oracle, and case B, X3 and X4 have been mislabeled. They have been labeled as class 1, whereas they are actually class 2. We computed the BBAs and applied the rule of combination twice, and we see that no matter the errors in case B, the belief of θ2 is always the biggest, even if θ2 is the less represented class in the neighborhood. For example, in case B, there are virtually 3 class 1 and 2 class 2, but still the class 2 has the most belief. So in the paper we studied two problematics. One, how does EKNN behave compared to the classical k-nearest neighbor, which would be called KNN, and second, how does EKNN behave with wrong labels? So in the first scenario, all labels are correct. It is just about comparing EKNN to KNN. The second scenario, however, takes the oracle's mistake into account. We will use the balanced accuracy as the performance score because it is more fit to take unbalanced distribution into account. This score is computed after each query, after the oracle provides the label during the active learning phase, and the number of neighbors is always a sensitive case, as a greater value of k can make the classifier too sensitive to noise. So we decided to fix it at 5. And here we have the dataset used in our experiments. So the dataset here are from the UCI database. We will also use the uncertainty and random sampling. The uncertainty described earlier, so the least confident rule, and random sampling will be used in addition to uncertainty sampling in the comparison between EKNN and KNN. The performances will be seen through the learning curves of balanced accuracy, and the protocol of splitting the dataset is given here. We have the initial dataset here, which will be split into a test set and a training dataset. The test set will also provide the bootstrap, which will pre-train the classifier, and the rest of the test set will be used to compute the balanced accuracy score, and the training data is the pool from which the unlabeled data will be given to the oracles. And this whole process is repeated 20 times, such that at the end we have an average curve for the 20 experiments. So the first result is about the comparison between EKNN and KNN with K equals 5. The plain lines are uncertainty sampling, and the dotted lines are random sampling. The curves in magenta in violet are EKNN, and in blue this is KNN, and the bound around each curve is a confidence interval. And as you can see, EKNN is almost always superior to KNN, except for two datasets. So in fact, the classifier is still dependent on the dataset, like a lot of the classifiers. The second result is about EKNN with wrong labels. So the oracle provides wrong labels, and here we only used the uncertainty sampling as a sampling method, and so the curves in plain are the data and noise. I mean that every labels are correct, and the dotted curves represents the data who have been mislabeled. And we denote by noise rate the proportion of learned data which have been mislabeled. For example, a noise rate of 0.1 means that 10% of the training data have been mislabeled, and so on. And in this dataset, the dotted curves of EKNN is always superior to KNN's, except for a noise rate of 0.7. And we can see that the more the noise rate rises, and the more likely the dotted curves become decreasing, which is quite instinctive, because if you provide too much false label, then the performances of the classifier goes decreasing. And also, the higher is the noise rate, and the wider we can see the confidence interval is, which here again is normal because of false labels. Another results of noise labels here, the difference is that EKNN and KNN behave quite similarly, but when you increase noise rate to up to 0.7, which is a very bad case because that means that the oracle is very bad, then the EKNN is less affected by the errors than KNN, as you can see here. So to conclude, we used a classifier based on the theory of Dempster-Shafer in active learning. We used EKNN. We saw that the contribution of EKNN is not negligible in active learning in comparison to KNN and in noised environment. And however, this classifier does not model the imprecision, and we cannot really say we modeled the oracle's uncertainty in a direct manner. So further works could be done on designing a more adapted belief function based based classifier for active learning. And thank you for your attention. I would be honored to answer any question you might have.